All right. Yesterday we looked at bugging, and we said bugging is basically having base learners of decision trees on aggregated samples, which are called bootstraps. Then after that, we aggregate the predictions. Remember, you are going to do sampling on sample. I mean, you are going to implement model on sample one, sample two, up to sample n. Then once you've gotten the predictions of each and every individual data point, you now proceed by finding the aggregation. Then after aggregating, you find the mean, and that is what we talked of when we talked of bagging. One of such models we referred to as random forest. Now today we want to talk about boosting. And boosting, I do not want to call it an advancement of bagging, but it might sound so. So this is a technique that builds an ensemble of weak learners sequentially, with each consecutive learner trying to correct the error of one that precedes. So what is happening actually is that we have the base learner, then we have the meta learner. The meta learners are referred to as weak learners. By weak learners, it means that we tend to use a model that is somehow weaker as compared to the one that we use in the base learner. For example, K nearest neighbor, if you compare it with support vector machine might be stronger. So we can use support vector machine to be a base learner. Then we use K nearest neighbor to be a weak learner. Then after that, we use another one, which can also be a weaker one than the second one. So let's use support vector machine, decision tree, and K nearest neighbor. So we might start with support vector machine. Then after support vector machine, we implement a weak learner, such as a k-nearest decision tree, a weaker learner. Then we also implement another weaker learner, such as k-nearest neighbor. So what we are trying to do, actually, the second weaker learner is trying to correct the error of the first weaker learner. But at the end of the day, most of them are weak learners. So a weaker learner is a model whose prediction is only slightly better than a random guess, and a base learner is any individual model in an ensemble. So boosting adopts a sequential approach where the prediction of the current model is transferred to the next one. So the next one, the next model, the next weaker learner is not actually going to take in the data set as the data set is not going to take in the data set as its what can we as the training data, but the prediction of the previous model. So each model iteratively focuses attention on the observations that are misclassified by its predecessor. Look at the last word. Each model iteratively focuses attention on the observations that are misclassified by its predecessors. So it means it tends to boost where the predecessor failed. Yes, that is it. So look at this boosting in a sequential approach. I want you to be very keen on this. We have sample one, sample two. The original training data is put into different samples. We have sample one, sample two, sample three, and sample n, up all the way up to sample n. Then we have a first base learner one, base learner two, base learner three, base learner four. In random forest, we just took sample one, decision tree one, decision tree two, all the way up to decision tree n, get to aggregate. Look at what is happening now. We are implementing decision trees, but we are starting on the first sample. So decision tree one, the predictions are then moved on to decision tree two, which is also done on our second sample. Then the prediction is moved to decision tree n, decision tree three, all the way up to decision tree n, which is a final model. That is the model that we can say has been well boosted. So n models are built sequentially. The output of the current is passed in as input to the next model. Then after that is when you find the results aggregation, then the final prediction. So the only difference lies in that there are some sequential outputs that are happening here, as opposed to bugging or as opposed to random forest. So here, the first base learner, the output of the first base learner, that is the predictions, are taken in as the input of the second base learner, so that the second base learner can scan through and find out the classes which had been misclassified and try and correct that. If it finds it out that it also gives an output, maybe that has been somehow boosted. So we might experience a slight improvement in accuracy. Then this one is taken in as for the third one all the way up to nth one. After that is when you aggregate the results. Yes. Because first of all, the models that are accurate are the ones that are being used to start building uh, the they're the ones that we use to start building the model itself. Take for example this case. If your data is, let's say, your model has given a prediction of 62%, that is a weaker model, has given a prediction of 62%, then you come and implement a stronger model on top of a weaker model. It might be somehow confusing. That's a very important question. But if you implement a base model that is a stronger model, it means that you can even stop at that point and use the results and use the results to make reports after implementing the stronger model as the base model. So the reason why we're using the weaker model is that the weaker model is now actually leveraging on an already existing stronger result. Uh, it is not weaker per se. It is weaker in the sense that it cannot predict the model better than the base model would predict when you use it on the original training data. So it might work best on an already predicted data, just to correct, to try and implement or to try and correct some errors. And by the way, it works. So that's how boosting works. So it basically tried to boost what the stronger model had leveraged on. And that's why in a football match, when we have a final, the coach always starts with the first 11 who are stronger enough. So unless they are tired, they're not tired, that's when the coach can bring in a weaker player. So that's the sense. The stronger team of 11 players are to start by maybe scoring. So these weaker ones, one letter to ensure that the time is exhausted and the play is done. But again, they are supported by the stronger ones who are remaining in the pitch. Exactly the same way as this model works. Advantages of boosting, and similarly to bugging, boosting is easy to understand and implement. Furthermore, it does not require any pre-processing and can handle missing values in the data. Then it efficiently reduces bias because we are boosting, by the way. Then boosting algorithms prioritize features that increase overall accuracy during the training. This process reduces the dimensionality of the data, hence reducing the computation time. What we are saying is that feature importance that we talked about in random forest, boosting will only leverage the most important features and assume the less important features, so that at the end of the day we do not need to work with lots of features in implementing the model, hence reducing the computation time, and not just the computation time, also reducing the usage of our CPUs and RAM and everything. There's one that people love a lot, it's called XGBoost. I think it's up is hapo mbele yetu tutapatana nayo. Disadvantage of boosting. The sequential approach of boosting makes the next models correct the mistakes of its predecessor. So this makes the overall model vulnerable to outliers, which means that if the predecessor had misclassified an outlier as belonging to a class which is not its class, the booster will come in and misclassify this outlier into a correct class, yes, but it is an outlier. And you are going to see how a certain model called dbscan can be used to even capture the outliers, but that is under unsupervised learning model. So boosting is not scalable for the same reason as the sequential aspect. So you might say this, that the sequential aspect makes it scalable, that it can scale. Boosting is only limited to a few number of data. Why? Did we just say that it leverages the most important features? So it does not actually extend beyond all the features. That is what we are trying to say. But at the end of the day, it is also a very important technique. So let's look at different types of boosting so that we get to know how each and every one works before we look. That's why I did not touch on how boosting works generally, because each and every boosting technique has a way of doing its own thing. So the following are algorithms under boosting. We have ADA boost, XG boost, gradient boost, cut boost, and light gradient boost model, or light GBM. In this reading, I think we're just covering two or three, I don't know, ADA boost or XG boost, and to some extent a gradient boost. So what I always say, please go ahead and cover the next three that have not been covered in this reading. I think I've just covered, if not ADA boost and XG boost, and XG boost. So we have adaptive boosting or ADA boost. From the word adaptive, ADA boost is a tree-based boosting methodology where each consecutive base learner assigns greater weight to the observations incorrectly predicted by the preceding learner. This is what happens in ADA boost. We say that the base learner, we say that the learner, the next meta learner, what it does, it takes in the results of the previous learner. So during taking in the results of the previous learner, it means that there are some values which had been misclassified. That's why the accuracy is not 100%. So in that case, AdaBoost is, this one is a tree-based model, meaning it uses decision trees. So what it does, it it treats with a high level of respect, in quotes, the ones that had been misclassified, because that is what it is interested in ensuring that it is optimized. So, and after doing that, it assigns greater weight to the observations incorrectly predicted. So the observations that were misclassified, those are the ones that AdaBoost is focusing on. Then AdaBoost builds its first tree on training data that gives equal weight to each observation. First of all, when you start, it builds first tree on training data, and this first tree gives equal weight to each observation. Umeona hapo number one. Then the algorithm evaluates which observations were incorrectly predicted by this first tree. After that, it increases the weight for the observation that the first tree got wrong, and decreases the weight for for those that it got right. This process repeats until either tree makes a perfect prediction or the ensemble reaches the maximum number of trees, which is a hyperparameter that is specified by the data professional. So umeona hyperparameter hapo ni how many number of trees are you going to build on top of each other? That is what we are trying to say. Remember, the one that is at the root node is the best tree. So as you keep on planting another tree on top of the second tree, as you plant the tree in the root node, it is actually treating all the observations with the equal as equal. Hakuna mkate ngumu mbele ya chai, zote ziko equal. So in the next one, this is where now it starts treating the ones that it got wrong with some high level of respect. It does so until the accuracy is increased. And this is what is this number of trees that you are going to specify as weak learners are actually specified by you as a data professional. So grid search can help us identify the best number of trees. That is an hyperparameter. So once all the trees have been built, the ensemble makes predictions by aggregating the predictions of every model in the ensemble. So remember, in decision tree, I want you to get the difference with bagging. In random forest, it is the results that were done on each and every aggregate sample that were being aggregated. Here, the results that are done on each and every boosting level that are being aggregated. So the only difference between bagging and boosting is that in boosting there is sequential, things are done sequentially, where the present one is correcting the errors of the previous one. Adapt boost on classification. For classification, the ensemble uses a voting process that places weight on each vote. We are going to see voting. Base learners that make more accurate predictions are weighted more heavily in the final aggregation. So we are going to see how voting works. Adapt boost on regression. For regression, the model calculates a weighted mean prediction for all the trees in the ensemble. What we are trying to say is that here is that the aggregation we talked about is for regression. But for classification, where adapt boost works best, we use voting. Just the voting, how we say it, how we just do it normally, that the person with the highest votes takes the day. That's exactly what happens here. The model with the highest prediction accuracy takes the day. And we tend to assume the model with the lowest prediction accuracy. So we take the ones with the highest, for example, let's say 80 to 90, then we find the average. That is, so I think I covered three. Adapt boost, adaptive boosting. What did we say? It tends to to focus more on those values that were wrongly classified, so that it assigns more weight onto those values. After that, we find the aggregation. In gradient boosting is different from adaptive boosting because instead of assigning weights to incorrect predictions, each base learner in the sequence is built to predict the residual errors of the model that preceded it. So here, each base learner in the sequence is built to predict the residual errors of the model that preceded it. And something is coming up here. Why are you not talking about meta learners? Why are we just referring to all these as base learners? Because the model that we're building, it is built, or it is taking in the output of the other data as a raw input for itself. So it is treating itself as a base learner altogether. It is not a meta learner. So here we only have base learners. So gradient in adaptive boosting was actually assigning weights in correct predictions, but base learner is predicting errors, residual errors of the model that preceded. So the residual error is actually y hat minus y. So it tends, you see, this error should be small. So gradient boosting tends to reduce this error so that at least at the end of the day, the residual errors are minimized. XGBoost, extreme gradient boosting. XGBoost or extreme gradient boosting is a popular and powerful machine learning algorithm used for supervised learning tasks such as regression and classification. It was developed by Tianyi Cheng, a data scientist at the University of Washington. Was that even necessary? But it was. So this one is developers go-to boosting model, and most of the time we've used it, especially if you are working, if you need an ensemble learner, an ensemble model algorithm that can work best on your supervised task. So if you are not going to take support vector machine alone, or decision tree alone, or k-nearest neighbor or naive Bayes alone, you can run to XGBoost. And let's see how extreme gradient boosting works. Remember, XGBoost is an ensemble learner, meaning it has base learners and meta learners. So this is the reason why it can be used on instead of a single algorithm. And let's see the key features that distinguishes it from adapt boost and gradient boosting, and the reason why we rush to it. Number one is speed. This model is known for its speed and efficiency, making it capable of handling large data sets. And that's the reason why it is being used. It can scale, it can handle large data sets accordingly. Number two is performance. It often outperforms other machine learning algorithms in terms of predictive accuracy. So number three is flexibility. It supports various objective functions and can be used for both regression and classification tasks. Then regularization. It includes building regularization techniques to prevent overfitting. Look at all those. So this is the reason why we run to it. How does it work? And that's why I focused more on ensuring that I explain some points on this model. Boosting. XGBoost is an ensemble learning method that combines the predictions of multiple weak learners, that is of decision trees, to create a strong learner. So what happens, this is now the one that we can say is actually boosting random forest. The weak learners give us the predictions. The next XGBoost is going to combine all these predictions. After combining all this prediction, it is therefore creating a strong learner on on these predictions that it has combined. Then from there, it is getting one final prediction. So we have, let's say we have decision tree one, decision tree two, decision tree three, decision tree three, and decision tree n. Both of them gives us predictions. Then XGBoost takes these predictions as the input data. Then from there, it gives a stronger prediction. And it also uses gradient descent optimization technique to minimize loss function, gradually improving the model's prediction. And what did we say gradient boosting do? We said that gradient boosting, yes, uh, we said that each base learner is in the sequence is built to predict the residual errors of the model that preceded it. So XGBoost, on top of making prediction, is also leveraging on gradient boosting to ensure that residual errors are also taken care of. So even if it is, remember, gradient boosting's work here is to ensure that we minimize the loss function. We reduce the y hat minus y. That's the residual errors, the predicted minus the actual. It is very dangerous for your predicted minus actual to be big. So this is why we say gradient boosting is used to minimize loss function. So it is used to reduce this error. After reducing this error, XGBoost comes in and build a stronger model on the reduced error. So you see why we cannot use gradient boosting alone. We can use XGBoost because inside XGBoost, we've used gradient boosting. Then why is it also powerful? It is an iterative process. It adds new decision trees sequentially, with each tree learning from the errors of the previous ones. So we do it iteratively until we are sure that now the last tree has actually covered all the errors sequentially from the first tree. Advantages, for that reason, it is highly accurate. It produces highly accurate predictions even with complex data sets. Scalability, it can handle large data sets efficiently and is suitable for parallel and distributed computing environments. See that. That's the reason why it is well chosen. Feature importance. It provides insights into feature importance, helping to identify the most influential variables in the model. Just like random forest, we are going to draw graphs to see which features were the most important ones. Uses. This guy has been used in cargo competitions. It is a popular choice among data scientists in cargo competitions due to its performance and speed. Then industry applications is widely used in various industries, including finance, healthcare, and marketing, for tasks such as fraud detection, risk assessment, and customer churn prediction. How I wish tunaweza pata data ya bank to build a model on fraud detection. Let me just try and find data so that XGBoost in the next building of models we do one on fraud detection. I think right now tumeivia sana churn prediction. And then there is no need of repeating things over and over again. So up to that point, is there any question you have on boosting? So that in this case, we are only going to build two models. We are going to build the ADA boost, which is the sequential guy, and then we build XGBoost, which is leveraging on gradient boosting, and that's why you see gradient boosting. We just touched on it because we were going to use it on XGBoost. Okay, so we shall build two models, AdaBoost and XGBoost. And nilikuwa najua building it too. So actually, but I really love XGBoost. And you're going to see why. And we are going to build, even if I find data for fraud detection, we're going to build it on the same data for churn prediction. You will see definitely the accuracy will somehow be greater than random forest. Not even if it's not greater, it can be just around that, but in most cases inakwanga greater. Because number one, why is it always greater? Because it is leveraging on gradient boosting, which first of all minimizes the loss function. You know, random forest does not have that capability. So after gradient boosting has minimized the loss function is when XGBoost comes in to do things sequentially. You build a tree sequentially and not just building a tree. The current tree is again correcting the errors of the previous tree, even if you build up. So at the end of the day, gradient boosting had minimized loss function. Again, the current tree is reducing more and more errors, and that's why it is proving to be somehow accurate. So let's talk about stacking, cascading, and voting because hapa kunanga models mingi. So next next time naona tukibuild lots of models. So you see why I told you that when I was at Savannah that machine learning in 1 month, because once you've gotten the theoretical approach, I think building the models become much easier to understand. Mm. There is stacking. From the word stacks. Stacking is actually borrowed from it's a development term. It's a development term, and it's borrowed from the fact that you can stack on top of each other. Stack evil. So at the end of the day, this one can sound similar to boosting, but let's see the difference, where the difference lies between stacking and boosting. Stacking, also known as stacks generalization, is an ensemble learning technique that combines multiple base learners with a meta learner to improve predictive performance. It combines multiple base learners with a meta learner. So we have a lot of base learners. Then you choose one as a meta learner. Then you combine these base learners with a meta learner. Stacking aims to leverage the complementary strength of different base learners by combining their predictions in a high-level model. The meta learner. The meta learner is chosen to be a high-level model. So this is where it differs from boosting. This allows for potentially improved generalization performance compared to using any single base learner alone. Stacking is pretty similar to boosting. The prediction from the base learner are stacked together. That's why from the word stacking, and are used as the input to train the meta learner to produce more robust predictions. But boosting, what was boosting doing? Boosting was actually taking prediction from the previous learner sequentially. But stacking, we stack together the predictions from the base learners. Then they are used as the input to train the meta learner to produce a more robust prediction. The meta learner is then used to make final predictions. Bagging and boosting typically use homogeneous base learners. Listen to this, and this is where we get it all different. Bagging and boosting typically use homogeneous base learners. If it is decision trees, all of them are decision trees. Whereas stacking tends to include heterogeneous ones. Graphical representation of stacking. We have the original training data. The original training data is actually split into samples. I don't want to call them samples, but it's split into samples. A sample n times the same training data. No. Wait, it is not split. What did we say? We said we use heterogeneous models. So we are not splitting it, and that's why you see we are maintaining the original training data. So we do not, it is not taking a sample, it is using the whole of the original training data. Yeah, look at that. Original training data, we are using model 1 to build, then model 2 to build, heterogeneous and different models, each one trained on the same data. So but in the other boosting and bugging, we were using homogeneous. That's why it was making sense for us to use samples. But here we use the original training data the way it is, except that we use it a number of times because we're using different models on this. So model 1, model 2, model 3, model 4. Alafu, after that, what are we doing? We are stacking all these predictions together onto a meta learner, which is another model altogether. So we can have decision tree, k nearest neighbor, support vector, no, support vector nataka niweke hapa. Decision tree, k nearest neighbor, neighbor-based classifier, and logistic regression. Alafu nakuja unaiweka kwa support vector machine. That is when we now make the final prediction. Which means that this model can work better than XGBoost, but there is a problem. It is always prone to overfitting. And that's why we tend to go to XGBoost more than coming to it. Advantages: it leverages the strengths of multiple high-performing models for both classification and regression tasks. Similar to other ensemble models, stacking helps build a more accurate model than individual models used alone. I think that's self-explanatory. Disadvantages. Look at the first disadvantage. Using complex basic models can increase the risk of overfitting. Different levels of the model's training can make the stacking architecture complex to understand, to implement. Yes, we are going to build it, but never ever make it your choice when you are hired. Because number one, the risk of overfitting. Kama kuna kitu data scientists fear is overfitting. While doctors fear a patient dying in their hands, for us we always fear a model being overfitted. Inafanya vizuri kwa your environment, environment. Then when you put it to the production, it is predicting to show a laptop, a high level CPU laptop. Huh? That is wrong. Shisho anafaa kuprediktiwa vitu za madawa za kiuno. Implementation in scikit-learn, we import necessary libraries and load the iris dataset. Okay, in scikit-learn there are datasets which you can use to just learn machine learning. But in our case, we're not going to use the iris dataset. You're going to use our own dataset. Then we split the data into training and testing. We define 3 different base learners, like a random forest classifier, a k-nearest neighbors classifier, and a logistic regression classifier. So imagine you're also using a random forest in stacking. That's why it is risking overfitting. You can even use XGBoost, you can imagine, but you're risking overfitting. So do not. It is not advisable. We define a meta learner, which is a logistic regression classifier in this case. So in this case, we've decided that let logistic be our meta learner. In short, logistic is the guy who is going to make the final prediction. Then we create a stacking classifier using the base learners and the meta learner. Then we train the stacking classifier, the training data. We make predictions on the test data using the trained stacking classifier. And finally, we evaluate the accuracy. We are going to see, and this example demonstrates how to implement stacking algorithm using scikit-learn. That is stacking. Jameni, sahi ukiulizwa what stacking is, you can know, sindio? We have blending. Get to know the difference between stacking and the one we're talking about, blending. Blending is an ensemble learning technique similar to stacking. Remember, in stacking, we were doing this, then stacking all the nini. Meaning, we had blended first all the models. The reason why it is coming to stacking, to be named stacking, is because we stacked all these blended models predictions, alafu tunaiweka kwa meta learner, then prediction. That is why it is called stacking. Now blending, in here, blending is an ensemble line technique similar to stacking, where multiple base learners are combined to make predictions. Up to that point, blending and stacking are on the same book. However, the key difference between blending and stacking lies in how the meta learner is trained. In stacking, the meta learner is trained in predictions made by the base learners on a hold-out validation set, which allows the meta learner to learn to combine the predictions of the base models to make final predictions. In stacking, we combine the predictions of the base, we stack the predictions of the base models to make final predictions. In blending does not use a meta learner trained on a holdout validation set. Instead, blending directly combines the prediction of the base learners on the training data to create a new feature matrix. It basically says that it combines the predictions of the base models on the training data. Then this one, from this, we find the most important features, and it is in these most important features that we again build a model. Then a simple model, often referred to as a blender, is trained on this new feature matrix along with the true labels. But in stacking, the predictions. In blending, a new feature matrix of feature. That is to say, we single out the most important features, and we use these most important features to build to implement a model on. Are we finding the difference where the two now break? The blender can be as simple as a logistic regression, linear regression, or any other suitable model for the task. The blender learns to weigh the predictions of the base models to make up the final prediction. So to try and explain more, you're just saying we have model 1, model 2, and model 3. So here, these three models, when stacked predictions, then meta learner. This is stacking. But when we have model 1, model 2, and model 3, we do not stack. We find most important features. Those are just columns that contributed more to the model's prediction. Then after that, form a new feature matrix. That is to say, form a new data set with the most important features. Okay. Feature matrix into bracket. This is actually new data set of most important features. Then you build a model on it, and this model is called a blender, and it's basically a meta learner. Then prediction. So you see where the difference lies between stacking and advantages. Like stacking and many other ensemble methods can boost the final model's performance in many cases. The use of this technique has been successful in winning many competitions. Because why should someone use it? Remember, we are singling out most important features. Disadvantages. During dividing the original data according to the blending architecture can limit the use of data for training-based models, hence resulting in poor performance. Then, like any other several models, the final model interpretability is reduced due to increased complexity, hence making it difficult to draw any crucial business insights. See how complex that model is. Na ukiona advantages inaongelelea vitu kama hizi, don't ever use such models. And by the way, the models we're just building today are preparing us for the second phase of this modeling, the deep learning. So which is hapo mbele, where we are going now to talk about introduce generative AI. We are going to talk about neural networks. So hapo mbeleni you're going to see. So this one here, these ones we are just looking at are just helping us, and that's why you will come across uh, a meme of a cartoon carrying something like, wanasema unaona deep learning amebeba kama tunyundo, alafu inasema by supervised machine learning and supervised machine learning. Thank you for helping me a lot. Meaning, it is highly recommended you get to understand the ideas of these ones first before you move to deep learning. Voting. I guess this is the second last one. Yeah, this is the second last one. Vitu zimekuwa mingi sana. But we are going to build models in the next 2 days. We cannot build all these models in a day. So probably tomorrow and another day, let's take this week to malizane na supervised iishe kabisa. Then we call it, we meet next week and start on unsupervised. Nataka by the mid of July, we will deploy one supervised model, one unsupervised model. Then I leave you to go to choose the one you're going to use for your midterm assignment. So voting. This is a technique used for combining the predictions of multiple base learners to make a final decision or prediction. It's just that, like the others, where we were combining different base learners. It is a simple and widely used method for both classification and regression tasks. In voting, multiple models are trained independently. Remember the way we did with the stacking? We train models independently on the same training data, and their prediction are combined to make a final prediction using either hard voting, soft voting, or weighted voting. So we are going to see what these hard votings are. Voting is effective because it leverages the collective wisdom of multiple models, which can often lead to more robust and accurate predictions compared to any single model on its own. It's commonly used in ensemble methods like random forest and bagging, where multiple decision trees are trained independently and combined using voting to make final predictions. So we've touched on this voting kidogo tu, nilikuwa in Adaboost. In Adaboost we said we build the models sequentially, then we use voting. So let's see how this voting helps. So voting is basically a technique. It's not, we cannot talk of it as an ensemble learning on its own. It is used by other ensemble learnings as a technique used by other ensemble learnings to make conclusion. Terminologies in voting technique, we have what is called majority voting or hard voting, and this is the most commonly used one. In classification tasks, it is used in classification tasks. Each base learner, which is a classifier, and base learners are respective models that you used. Listen to that. For example, decision tree is a base learner. Support vector machine, if used, is a base learner. Each base learner makes a prediction. Up to that point, we are together. And the final prediction is determined by the majority vote among all base learners. This means that the class with the most votes is chosen as the final prediction. So if you used support vector machines mbili, you use decision trees tatu, we make the voting. The class with the majority of votes ndiye anachaguliwa, and that's what we use to make classification, to make prediction. So that's majority or hard voting. Then we have weighted voting. It is similar to majority voting, but each base learner votes is weighted based on its performance or reliability. Better performing learners may have higher weights, influencing the final prediction more strongly. Why should we use weighted voting? In short, weighted voting is an advancement of hard voting in that, how reliable is this model? Hata kama imeshindwa na yule model ingine, but how can we rely on it? For example, if you have random forest and you also have k-nearest neighbor, we tend to rely more on random forest, even if k-nearest neighbor gave us a higher accuracy, meaning it was supposed to be voted in as the leader, as the winner. But we are going for random forest because number one, it scales Number two, accuracy is increased as you increase more and more models. Then we have soft voting. Instead of just counting votes, each base learner's prediction is assigned a probability score for each class. The final prediction is then determined by averaging these probability scores across all base learners and selecting the class with the highest average probability. What are we doing here? Probability inakwanga n all over bigger n. So after we are done with all these, classification tasks on we using individual base learners, we now start assigning probability. For example, decision trees, how many are they? There are two. Out of how many, the n number of models that we use 10, 2 over 10. So then a random forest, how many are there? It is 1 over 10. You wait until we are done, we are all the way up to the last model that we used. Then the final model is then determined by averaging these probability scores across all base learners and selecting the class with the highest average probability. But that is in classification. When you do it in regression, it is called average voting and not soft voting. Here, each value learns to predict a continuous value, and final prediction is the average of all base learners. So in short, soft voting is used for classification, where we do probabilities, while when you see average voting, it goes for regression. Regression, we said, predicts a value, a continuous value. When we have this continuous value predicted, we find the averages of all the classes. Then the final prediction is the average of all base predictions. So voting is a technique. It's not necessarily a model on its own. It is used alongside other models like random forest and AdaBoost. Are we together? You will find time and learn more on voting. So advantages of voting: it's simple to implement compared to stacking and blending. It also does not require complex fine-tuning. Just vote. Then using multiple base learners in the voting makes it less susceptible to the, how do we call that? Well, thank you, that one. To the influence of individual models, which contributes to making more stable and reliable predictions. Disadvantages: it can be difficult to deal with models prediction conflict, which makes it hard to make the final decision in a meaningful way. What if conflict means, what if we have two averages that are the same? Huh? What can you do? It can be very difficult. It makes it hard to make final decision because you don't know which one to choose. But again, that analytical mindset helps you choose one that you feel like. Then you start adding more models to the ensemble voting model does not necessarily improve the final performance. In fact, it takes you to the first disadvantage. It just improves it just increases the it just increases, what do we call it, the surface area of making the model's prediction conflict. I don't know how to put that point, but I hope you understand what I'm trying to explain. The last one is cascading. Do not worry, we're going to build these models pole pole. If you don't understand, you just be coming back to the notes and understand what it entails. Cascading refers to a sequential or hierarchy, hierarchical approach to building models where the output of one model is used as the input of another model in a cascading manner, that is, moving from one stage to the other. It is similar to boosting, that is, but let's see where the difference lies. This technique is particularly common in scenarios where the data of tasks can be broken down into stages, and each stage builds upon the previous one. Cascading can involve various types of models or at each stage, depending on the nature of the problem. That's the difference. Are we together now? So it is sequential, yes, but it's moving from one stage to another. So in cascading, what we do, remember in boosting, we mostly use decision trees. So for example, AdaBoost uses decision trees alone. Decision tree as the base learner, then it builds on the second one sequentially until you are done. But in cascading, we move from one stage to another, yes, but using different models. So it can involve various models or algorithms depending on the nature of the problem. So after you are done, let's say you umepata most important features and you feel like these most important features is not complex and I cannot use XGBoost, let me use a simpler model like logistic regression. That is what we call cascading. And it allows for modular and hierarchical approach to modeling where each stage focuses on a specific aspect of the problem or data. Remember, in short, each stage is independent. But in boosting, each stage was dependent on the previous one. In cascading, each stage is independent, and that's why we use a different model altogether. Implementation in machine learning, pre-processing stage. Should I explain what that this one is? Then modeling stage one, the pre-processed data is fed into the first model, which could be a simple model like linear regression or a more complex model like a neural network. We are going to talk about neural network model. By the way, neural network is an advancement of logistic regression, so, but you're going to see it. So nowadays, instead of using logistic regression, most guys use neural networks. So this model generates predictions or outputs based on the input data. That is stage one. Then immediate stage. The predictions or outputs from the first model serve as input features for the second stage. Additional pre-processing. See what? That's why it's called intermediate stage. Additional pre-processing or feature engineering may be performed at this stage if needed. The keyword is may, optional. So you are not forced to implement. You're not forced to implement additional pre-processing, like additional pre-processing. It is dependent if needed. Then we have modeling stage two. After you've performed pre-processing, that's why intermediate is not a stage because it is optional. Meaning you can just get from stage one to stage two because if you don't need to clean the data, if you're sure you had cleaned it well before, why should you clean it again? Here, the processed data from the intermediate stage is fed into the second model, which could be a different model or complexity compared to the first model. This model generates final predictions or outputs based on the processed data. So you see how it is done. So cascading is different from boosting in that we use different models at different stages. And as you can see, it is somehow, to me, I think it's somehow it's somehow a very robust model, except that these robust models are always prone to overfitting. Advantages. The next model is specialized in the output of the previous model, which reduces noise in the data. Then more robust to overfitting and can perform well on real-world data. Okay, correction there. Then disadvantages. Implementing the cascading can be complex since it involves training each of the models in the sequence. Umeona vile iko complex. Then getting the optimal cascading architecture can require a lot of experimentation and fine-tuning, which can actually be a toll on our operation side of building the model. We mean CPU, memory, and RAM. Just experimenting. Can I use this model? This one is not working well. Let me try that until we find the best one. Tulishare some about metrics. We're not going to do about that. We said to measure regression models accuracy in machine learning, we use coefficient of determination R squared. Can you remember what you said about R squared? Hey, stop it, please. I just wanted the word variability, and that's what does it. Is the percentage of variation accounted for, accounted for by the dependent variable on the independent variable. So, like how much does the independent variable affect the dependent, right? But it's okay. So ingekuwa kwa interview hiyo ungekuwa umepata hiyo tick. Mean squared error, MSc. Okay, okay. Please don't continue. Okay, in short, it is variance. Mm. Mean absolute error, MAE. Okay. This one, this one could be new. I know. You see the residual minus the actual y hat minus y. See, tulisema sometimes it can become negative. So you find the absolute of that negative. So the absolute, you do not, then after that, you do not include negative. Then after that, you find the average of everything. The average, that is what we call mean absolute error. So you first of all you assume operation signs, you assume negative sana sana kwa sababu kiadi itakujanga zero. So also after assuming negative, you start adding all of them as if they were all positives. Then you find you divide by the number of observations. Then that is what we would call mean absolute error. So this value should be small also. There are two ways to measure classification models accuracy in machine learning: confusion matrix, classification measures. And we add accuracy, precision score, F1 score. Coefficient of determination measures the percentage of variation in the dependent variable y explained by the independent variables x. Same hivi kwa interview, get your 2 points and stand out among the interviewees. Wish me well. I just sent my, so is this. Sorry. The recruiting officer at Safaricom just gotten his contact and we exchanged some. I gave him my CV and he was like, "This one looks brilliant." So wish me well. I hope everything goes okay. Yeah. Even I had it in mind that if I get that, I had even seen Shaq as the one managing market share. But let's just wait. Okay, then we also have used mostly on linear regressions. Mean squared errors, MSC, and root mean squared, I think we talked about this, is the average of square difference between the predicted and actual. So a smaller value is considered and a good value is sure that there is no greater difference between the values. Then mean absolute error, see what I was telling you, the formula there, you remove the negative and use the summation of y minus y a hat, then you divide by n, the number of samples. And just like that. And this one, a lower I mean gets better performance. Nimesema hivyo that this value should be small. Confusion matrix and n by n matrix used for evaluating the performance of a classification model, where n is the number of target classes. So I think tumeshindana tukisema more about confusion matrix and but tulimalizana kwa hizo notes zangu kweli. We should revisit it. Tomorrow to build model, we shall revisit it. Please remind me. Yes, remind me. We have to understand the theoretical approach to it very well. Then next week, tutaanza unsupervised machine learning. Yeah, and that's what I had from chumba cha wanahabari today. this is shorter as compared to the guy. Oh my god, I love DB scan. Okay, we are also going to talk about the research, more of it. Hey, it's just the same one. Okay, a priori algorithm. Jamani, FP3 count on the item. I thought in Kadogo, this one. Hey, are you prepared for maths? You have lots of maths coming. Yes, and see why advice cannot be ignored. Look at real world examples: anomaly detection, recommendation engines, customer segmentation, fraud detection, natural language processing, genetic research, then reinforcement learning. Reinforcement, the idea reduction. Hapa siangaliki sana, but we also build some models. But hizi tutafanya after nini, then we get to deep learning. I know you cannot wait for this.